Hi, I'm Maddie Pelshaw.
I'm Akila Chapman.
I'm Jennifer McManus.
Abby Amy.
Samantha Norman.
So our project focuses on a small-scale water filtration system modeled after the natural filtration provided by wetlands. And our project would theoretically be used for greywater reuse and treatment, as well as for educational purposes in the natural and sustainable sciences. So this is a brief overview of what we'll be talking about today. Our project was inspired by a couple previous projects on constructed wetlands, one being at the John Hines Wildlife Refuge in Philadelphia, and the second being at the Areva Institute in Palestine, which was a constructed wetland built for providing fresh and clean water to a low infrastructure community there. So this is an example of a layout of that system. So the greywater would be pumped into the system, go through a series of artificial beds, and the filtered water would be collected, and in this case would be used for irrigation and for toilet water. So our project would be smaller scale and would be used for urban schools. So we feel that our project meets these sustainability goals, one being quality education, because there would be science programs along with the installation of this system, clean water and sanitation, and reduced consumption and production, as this is a low energy water filtration system that provides clean water for a second use in the school. And we feel that with grants, it could also lead to reduced inequalities between education at schools, as underfunded schools could still apply to be a part of this program. So wetlands only cover about 6% of the earth, but they provide 1/3 of natural carbon storage worldwide, as well as providing 1/4 of our ecosystem functions globally. So what does that mean? Basically, I think that it means that wetlands are the single most important type of ecosystem that we have in terms of the functions they provide us, such as atmospheric maintenance, in natural pollution remediation, and also water quality maintenance, flood prevention, habitats, and natural biogeochemical cycling of nutrients. So we feel that the water quality improvement and atmospheric maintenance that wetlands provide could be reconstructed in an artificial system. And so in our setup, the sinks and shower water in the school bathroom would be rerouted to this artificial wetland. It would flow through a series of gravel and sand beds, and the low permeability of this system would allow particulate matter to settle out. The soil provides an environment for plants and microbes that coexist in their roots. And these microbes are capable of removing nitrogenous compounds, phosphates, which are common in soaps and shampoos, which would be completely relevant for the sinks and showers that the water would be coming from, as well as heavy metals and even pathogens. And the plants also not only would provide the environment for these microbes, but would take up their own nutrients, remove carbon from the atmosphere, and be aesthetically pleasing for the urban environment. So the water would filter through this system, and the clean water would then be rerouted back into the school's bathroom for use in toilets.
So these are the materials that we found to be commonly used in constructed wetlands. So the tank is often made of fiberglass, polyethylene, and reinforced concrete. The liner can either be polyvinyl chloride, PVC, high-density polyethylene, HDPE, or UV-resistant butyl rubber. The piping is usually made of PVC, the filler gravel, sand, and soil, and the wetland plants listed are all native to Pennsylvania. So we'd like to use native plants to maintain them. To make our project more sustainable, we looked at using upcycled materials to construct the wetland. So polyethylene is the most viable for the tank because it's more easily recyclable than the fiberglass, which would need additional components added to make it useful, and then the reinforced concrete couldn't be recycled. Unfortunately, we couldn't find a vendor that specifically makes polyethylene bins at the moment, so that's something to look into in the future. But you can upcycle polyethylene into sunglasses, carbon nanotubes, and water jugs. We could also use old tires possibly, as the U.S. has a plethora of old tires, but we would have to look further into regulations to see whether that would be compliant. For the liner, we could use upcycled PVC, HDPE, or the butyl rubber, because those could all be made into mesh. As far as the pipes, upcycling PVC is possible, but using old materials isn't allowed due to regulations because of possible cross-contamination. So we couldn't use it in our system for that purpose.
Okay, so I want to talk a bit more about the more technical aspect of this project. And so in the fact that we want to be cleaning the water, we will also have sensors put in at the very end of it to test the actual quality of the water. And so a large part of that is going to come from the breadboard, which acts essentially as a mini computer, and all the sensors would be connected to it, and then the data from there will then go to an online program or an online database. So these are the 4 main sensors that are available now that we know that we would be using. There's pH, electrical conductivity, ORP, and dissolved oxygen. These all work similarly in that they run a sort of voltage or a current through the water, and they use that to manipulate it with equations to get the actual values. For the pH, we found that the values that we calculate need to be specifically between 6 and 9 so that it's not toxic for the plants. And then for electrical conductivity, this is generally used as a stepping stone for like multiple nitrates. So we found that sodium is something that we would need to keep on track of, but there is no specific sodium sensor. You would adapt the electrical conductivity to do that. And then also pH and EC are like things that are often tested, and they're very, very strong. And in most breadboards, they need to be on separate circuits because running the information on the same wire can contaminate both sets of data. And then phosphorus. So phosphorus is super, super important in looking at the quality of the water because it can affect both the plants that are within the system and plants in the natural environment. And this is something that we find a lot in greywater because it's in soaps, shampoos, et cetera, et cetera. There is no current sensor or like method for testing phosphorus separate of going to a water treatment plant. So that's something that how this project would need to grow. And then, so here demonstrated is what the sensors might possibly look like. Here on the left are 3 sensors put together in water. And for this, we just wanted to make sure that the sensors are working. And then on the right side is a sample of how they would be set up on the breadboard. And on this breadboard, the pH probe and the electrical conductivity probe are, in fact, on 2 separate circuits. And then, so there's also a very strong coding component to the project. And so here on the left is a sample code for a pH probe. And here you can see that it is already collecting data. And then on the right is multiple different probes set up in a similar system that we would want to build, continuously graphing data so that the students are able to do data analysis in real time.
So for the other side of the education part, we decided to make kit type things to give to the schools to help further the learning of the students and kind of help the science teachers guide how they're going to learn. You can see from the 2 sides of this that we adapted it for both middle school and high school because those 2 grades of students are going to have to learn different things because of what they already know and what they're able to understand. So you could see from middle school, you're learning things about the water cycle, problem solving, like how and why it's important to recycle, where in high school, those are things that they're going to most likely understand. So you get into the more technical aspects of coding, as we were talking about with those other things, to analyzing the data that comes in through those different probes, to the actual construction of the system, which is something that from the kit that we would give the schools and the students would be able to do. So it was important to have these 2 things to give schools the chance to start from a younger age and have them grow with the system itself so that way students can be interested in science and maintain their interest in science as they get older so they can all eventually become children like you. So in part of that aspect, I wanted to mention the skills that were going to be learned from the high school level. You have soft skills like collaboration and confidence all the way up to coding and data analysis, which is something that not every high school student is going to learn how to do. So from this system, they're getting something additional than what they would usually be learning in their schools, which to our group is something important to like be in schools and to help maintain sustainability. And then for the grants aspect of this, we understand that this system can be a little pricey for a lot of schools, especially for a lot of underfunded schools in Philadelphia. So if you were to either simply Google it, there are thousands of science grants available from the government, from private companies, from charities. There's a whole bunch, anything from like math to science to STEM specifically. So if there was a school or a teacher or even a student that was very interested in this project, they would be able to go and try to find a grant for it to help subset some of the costs that might be there. And then it's also helpful if you were to get some partnerships with professional organizations or universities, so we can try to get some of our customers in some of the schools from the contacts that we have at Drexel or that Drexel has in general, but also to help those students. So you could have a college professor like come in and maybe teach one of those lessons, so those high school students see what college is like, and along with keeping them interested in science, like keeping them interested in like continuing their education, so that way they can like further along and like help the planet.
So as Abby was mentioning, our target audience are the city departments of education and science teachers. So we were looking to pitch the idea at schools that are either being remodeled or newly built. And we do that by attending science conferences and city school board meetings to put our idea out there.
So initially we wanted to target schools that were already in existence, but we determined that the cost of having to potentially redo the plumbing there would be great, upwards of like $10,000 in addition to our kits, as you can see from this table here. The total price we approximated was around $1,600. So for future work, we determined that it wasn't going to be feasible for an urban schooling, considering that Philadelphia itself has a hard time being able to provide just a general science education to their students. So we determined that it wasn't going to be a feasible project for them, given with the $1,600 cost of just the kit itself, and potentially the grants not being able to provide enough assistance to them. We're looking into investigating more affordable materials, like potentially being able to just find like sand and gravel that's kind of laying around that like other construction companies like aren't really using and looking to get rid of. In addition to potentially just using like plastic bins that aren't that are like kind of lying around the school rather than having to go out and purchase the tires, and potentially research more improved compliance with regulations of the EPA and potential that rubber leaching into the water. And the phosphate sensor, even though it's not in development, it'll add a cost to the kit when they purchase it.
Okay, I have a question or comment from Juliet, the director of Iceland School of Energy. She said the wetland idea is really good. There's a lot of concepts and possible areas for learning. She suggested there's a whole section of learning that hasn't been covered, although you might have mentioned it, and that is the plant growth process. The difference that this might make is it collecting air temperature data, rainfall data, and maybe pressure as well, all easy to collect and possibly related to plant health and growth rates. As you said, anyway, nice idea.
Thank you.
Also, as a side note, a wise woman once told us that being able to like build something that naturally occurs in the ecosystem is priceless. Like that naturally does things for us is priceless, and like if you try and manufacture it yourself, it could get very pricey very quickly.
The wise woman.
You can't. Exactly. Any other questions, guys? Yes?
It's just like a logistical question in terms of implementing this into schools' curriculums. For high schools, can it stand alone without being implemented in middle schools, or do you have to have both?
So we adapted it so you could either do it either way. So like, because they're all so different things, there's only very few things like the actual construction of the thing that would actually overlap. You could start. The idea would be to start at middle school and go to high school. But like, if high schools were like, we don't like middle school that much. High school, they could start there and still be able to understand everything from the beginning.
So I really like your guys' idea of using native plants for the local areas, especially as people are developing urban areas more and more. I think life into doing this amazing thing with filtering the water. So for a more broader perspective of wanting to move into other regions or other markets, how would you see using those similar plant systems but tailoring them to the local plant species for different, like an outreach region?
So wetlands, although only 6% of the Earth's surface, they are found in many different regions. So as long as you are able to cross-reference aquatic plants of that region with remediative plants, then you can still do this system. And as I mentioned, this system was carried out in Palestine, which is a very different region than Philadelphia, and it was still able to work and provide this service to those people. So I think it could be adapted. You just need to do a little more research per region.